Good afternoon. It's my great pleasure, to be introduced by two of my friends, Wolfgang Hedler and Professor Ray Carroll. So Professor Carroll said we have exact 11 years apart in academia. He's certainly 11 years younger. And so he was professor at the University of North Carolina probably 11 years before me. And he was also a COPS President of War 11 years before me, and he was Humboldt Prize winner 11 years ahead of me. And but he was 11 years younger than me. And it's really my great honor to have a chance to talk on Hermann Otto Hirschfeld lecture. I know H.O. Hartley. Today the first time I equal to person, and so it's really a great honor. And Wolfgang actually asked me to talk on finance because officially now statistical title at Princeton for me is illegal. My formal title is Frederick Moore Professor of Finance. So that's how I talk on the finance, and is really a lot of my own work based on two giants. Ray Carroll and Wolfgang Hedler, and they certainly, just like Ray said, make me feel bigger too. And it's also a great honor to be the Humboldt Prize winner, and so we start our collaboration between Princeton and Berlin, generally speaking. And I know that like your university here, Princeton also have great tradition. We have church too, not as pretty as here, but also very beautiful. Usually I come to church not because I'm speaking, usually it's our president's speech. So today I have an opportunity to stand here to speak. I feel very honored. So today my talk is based on option pricing with aggregation of physical models and non-parametric learning. So since the publication of well-known Black-Scholes formula, there's a lot of extension in mathematical world and the financial world on extend the flexibility of Black-Scholes model. That is, you could imagine Black-Scholes model is always based on geometric Brownian motion, just like a linear model in statistics. And so people enlarge, let's say stochastic volatility, enlarge, the dynamic of physical models. So this is on one hand a development. And on the other hand, when financial econometricians come in, so they also say, okay, you have option price traded frequently on the market, and at the same time that you have option characteristics. So you could say, okay, let me do, let's say, statistical learning or non-parametric learning. Then you could also build an empirical pricing formula. And these two seemingly unrelated, and my talk today is trying to marriage the two worlds. And I try to please both communities, and maybe at the end, none of them like me anyway. So here is my outline of talk. So I'll talk about option pricing using regression approaches. So I'll talk, parametric guided, non-parametric estimate of state price density. And the main thing here is to mathematically combine the powers of physical models and the empirical methods. And all of our methods, not like some of those models, are very computational intensive. And some of those maybe even not enough to give traders enough information so that they can make wise decision. Being in Princeton, close to New York, I'm very fortunately that I got different kind of consulting project from credit risk to equity risk. To talk about, to all of these. So I know some part of their culture, and therefore I try to bridge the gap between industry and academia too. So I'll talk also on non-parametric estimation of implied volatility, and that will give me another procedure called semi-parametric estimating of state price densities. And then I'll talk about ad hoc Black-Scholes methods, and the judgment of the day certainly is empirical studies. So see if I can come out with some numbers that will interest some of my friends on the street. Okay, so here is the question, right? So the basic question is value contingency claims, that is financial derivatives. So my talk today mainly based on option pricing, but it doesn't surprise me that one day you could apply this to, bond pricing, apply to these two CDOs. And I know that Merrill Lynch made a lot of money over the last 3 years. When this summer I had, just like every year, I organize financial engineering meeting, and everybody tell me this is the hottest and the most lucrative areas. And now Merrill Lynch lost $8.4 billion this quarter, and that probably also gives some alarms that maybe those guys are very smart, but nevertheless they miss something that in pricing the risk of financial derivatives, and maybe they could come back and ask us, and maybe people here are able to help them do something better. Okay, so the call option, as everybody know, I know there's a very diverse audience here, give the right to buy certain asset, let's say the DAC index at certain price, K, which we call strike price. And for index, it's usually European options. That is, you can only exercise your right as expiration time. That would be European option. And if you have right to exercise any time before expiration time, let's say 3 months from today, then this is the American option. So the payoff function of such a kind of financial derivative is, if the asset price bigger than strike price, then you gain something. Otherwise, you got zero. So you got a non-negative. Payoff function, which is really like this step function here. This function here, it pays zero and then increases. So therefore, I give you rights, I give you non-negative payoff. I ask how much you should compensate me, just like the same way you do insurance. You buy insurance, the other side, incur the risk. You ask what is the premium you should pay. And similar kind of thing actually also occurs very frequently in financial world, like mortgage-backed securities. Somebody wants just interest rate between 7th year and the 9th year, and so on. So this is always a very complicated, financial derivative. But nevertheless, let's look at the most vanilla type of option first. That is pricing the option at for European options. Okay. So similarly, you could define what's called the right for sale. That would be put option. Put option is basically give you right to sell at certain price, and the payoff function would be just like this. And you could do linear combination of these kind of things. That would be very similar to kind of CDO. Collateralized debt obligations. And by combining these, you could get a step function, and therefore you could approximate any payoff function you like, as long as it's Europeans. So certainly there are lots of exotic options that I'm aware of, like, and we talk, on Saturday and Sundays, Asian options, look-back options, that is path-dependent options, and barrier options, and so on and so forth. So this will be like my focus today. So all really we need to know for my talk today is a very complicated, financial, mathematical formulas, but all really you need to know for my talk today is this pricing formula. That is what is the, if I have you give me the payoff side depending on the the terminal, let's say, assets value. What this value is the discounted expected payoff under risk neutral world. That is to say that this is the expected payoff starting from today, and 3 months later was my stock move, and you calculate under risk neutral world, because we are talking about different kind of hedging strategies to replicate the whole price. So it's a comparative pricing rather than absolute pricing. That is, we do not ask ourselves as economists where the price comes from, but rather we basically say, well, if there's a price and there's a derivative, what does it cost? Anyway, so this is the discount factor. From today to T years later, the cumulative interest rate, and this is the expected payoff. So now let's see what this pricing formula depends upon. So if we look at it, it depending certainly upon option characteristics, right? So it depends on strike price because this is reflected in this payoff function. So if we go back one slide, so the payoff function depends on the strike price. Depend on the time to maturity because I mean starting from today where my stock will wander into, and certainly depend on what today's stock value, so this is initial stock value, and depend on interest rate. So for this talk, I mean, I'll assume interest rate is constant. And in pricing mortgage-backed security, which we call interest rate sensitive financial derivatives, certainly everything is the risk of interest rates. So in that case, assuming it's constant probably is not very realistic. Okay, and the most importantly, if I really want to compute this expected payoff under risk-neutral world, I need the conditional density, that is transition density. Given today's stock is $30, what is the chance 3 months later it becomes $40? So this is the conditional density, ST, which is the key on my talk today because once you have this, you could price any financial instrument you like. Okay, so and this density has a special name. Most people know, probably called state price density. It depends on what state of my stock, how much you pay me. So that's how it calls state price density. And so which is really the density of assets under the risk-neutral world. And in a more technical jargon, it really says that is the conditional density or transition density 3 months later of assets given today's stock value under the current Martin Gales. So, so this is just a technical jargon, but probably is not matter. So the nice thing of this guy is directly related to the pricing of any financial instruments because all you really need to do is compute this conditional expectation. And I mean, so it's independent of payoff function and is very useful to evaluate, I mean, illiquid trade financial derivatives from liquid trade financial derivative because you could get market implied financial, I mean, the transition density and using these two price, I mean, illiquid trade, I mean, financial derivatives. So if you look at the Wall Street journals, I mean, how do they blame Merrill Lynch's loss? I mean, they will say, well, the loss of derivatives there are not frequently traded, so therefore they don't know how much value it is. So certainly they could use, I mean, if they are willing, they could use liquid trade financial instruments to imply the transition density, and using that, and now you go back and price the financial instruments. So this is the power of transition density. Oh, by the way, stop me anytime because my speed tends to be faster and faster as I go along, just like you're running faster and faster. So in a very situation, which is familiar to all of us, is Black-Scholes, I mean, formula. That is, if the stock assets price under the risk-neutral world follows geometric boundary motion, that is, the percent of return has instantaneous rate R, which is the risk-free interest rate, and then plus volatility of this stock, then we knew that by applying Otto's formula, the log of my, I mean, just like you take a log if you do naively, a log of my assets price would have a solution to this stochastic differential equation depend on boundary motion. And so this is really would be normally distributed with mean this and the variance this, right? Everybody knows that. So we know that the transition density under Black-Scholes model, it would be log normal distribution with mean, given by the risk-free interest rate minus volatility and the variance here. Okay, so we know this special situation. So let me just give a formula so that let me denote this transition density as log normal density, which depending on all option characteristics. But for simplicity, I'll just say stress dependence on volatility. Okay, so now according to the formula we says, what is the option price? It will be discounted, right? Expected payoff. So there's no payoff if stock price state is less than K. There will be payoff from K to infinity, and this is the payoff function, and you do averaging with respect to state price density, and you get the Black-Scholes formula. So let me write it as pricing Black-Scholes and depend on volatility. So BS is stand for Black-Scholes here. Okay. So now in the, in the Wall Street, certainly everybody doesn't like to quote on the, the option price. So they just regarding Black-Scholes formula as a calculator. So you, if I give you the option price, you have option price, so you apply, you plug it into Black-Scholes formula, you invert it, you got what's so-called implied volatility. So implied volatility, just like trader usually to say, is that you plug in something into a wrong formula in order to get the right price, right? So this is really the implied volatility means. So just, but it's a nice thing, therefore, for trader to understand. Just it's a transformation, mathematical transformation. So certainly, we all know that there are many studies, plenty of those, thousands of those, show that, there's lots of evidence for inadequacy of Black-Scholes formula, and that's usually what's called implied volatility smile. So what I'm plotting here is the implied volatility surface against two things. One is moneyness, and the other is time to maturity. So we can see the smile. So it's from moneyness, from high to low. So the implied volatility is high, at money getting lower, and increases. Right? So each of those have these kind of implied volatility smile for different kind of maturities. So this is all very well known. Very well known. Phenomenon that or you could even say the style feature of financial market. So now what is the moneyness? So the moneyness in my talk today is just the strike price relative to the future price, right? So this is the spot price, and then this is the time to maturity, tau or t, whatever, and then you have risk-free interest rate subtracted by the dividend paid by the stock. So from mathematical or statistical point of view, this is nothing but just normalization. Basically normalize all stock to have $1 or the future of the stock to have $1. So one thing, automatic to it is that it accounts directly the interest rate and dividend paid by the stock. So this moneyness is one of the things that people use. So for my today's study, I realized that the time to maturity, is limited. It's quite discrete. In other words, you have standing on today, you may have 3 months, 6 months, 9 months, 1 year, and maybe you have 1 month or 2 months. That's probably it about the option traded in the street. So it's difficult to aggregate. I know that there's a lot of work in this Heidelberg, in this Humboldt-University on estimating the volatility surfaces. But nevertheless it's difficult because you have only 5 or 6 time to maturity. So it's difficult to use non-parametric together without making some kind of error. So therefore, for today's talk, I fix time to maturity approximately. Let's say I just follow the options with, let's say, 6 months time to maturity. So this gives me one advantage to fit individualized volatility curve just or state price density for that particular option, let's say 6 month option with expiration of 6 months. And this certainly gives me, minimize the chance of modeling error, but of course there's always a penalty. That is, I have less data now because I only use maybe 1/5 of the data. I only observe the option with time to maturity about 6 months. So in order to, increase back about the same amount of money, the same amount of data. So let's say standing on today, I go back 1 week. Okay, so I go back 1 week. So this gives me 5 days data for this option which traded on, and for this 6 month option. So I have now 5 days data which times 5. So I will get what I will get. I will get the moneyness of that option, and that is 6 months time to maturity, and is implied volatility. So I will get the data looks like this, which is usually about 150 to 200 data points. So in implementation, I'll just take 1 week from today. And this is what people typically do in Wall Street, and they do a little bit modified of that. So this is what's called the quadratic fit, right? So because of implied volatility smile, here, implied volatility smile here, so you fit a quadratic function to it. And again, I'm fixing time to maturity about 6 months. I only follow one particular option rather than follow all 5 or 6 options. So there's only curve in my fit. So if you fit a quadratic curve to take into account of volatility smile, that is, you fit a quadratic function to it, and if you run the regression with the coefficient A0, A1, A2, you got your fitted quadratic functions, and now you again plugging into the wrong formula to get the right price, you get option price depending on your moneyness. So this is the usually people do. So, and this is really a benchmark routinely used in industry. There's a lot of good things saying about it, and in particular, like Hastings and Nandi, they introduced gauge type of modeling, and they conceded that actually gauge type of modeling not only computational is more expensive, but also at the end of the day, it doesn't give any better pricing formula than the ad hoc Black-Scholes. So now here is how does it work in the empirical data. So we took the last week in 2004, and I look at the time to maturity between 107, that is about half a year. As I said, I really look at for half a year, but I back for a week to aggregate the data. And this is the plot here is moneyness against implied volatility. And if you fit a quadratic curve to it, because quadratic curve is global, if you fit something here, you will not fit something well here. So there's a lot of trade. Trade is very liquid for moneyness around, and money, option is very, very liquid. So if you go a little bit beyond that, there's the fit is not very, very good. So for those people who are doing here, non-parametric or semi-parametric, people say, okay, so now the quadratic doesn't fit well, so why don't I just do a non-parametric smoothing to it? So this is the blue curve that I draw here. So if I do non-parametric smoothing here, then I will get the implied volatility function, and I could also plug in into Black-Scholes formula. So the only difference here is Q now replaced by non-parametric fitting rather than parametric fitting. So this I will call this as a semi-parametric approach to the model, because we're still using Black-Scholes as our guidance. So this is basically what it does. So now let's see, this is one of the methods that we do, which is closely related to Aissa, Halia, and Lowe. So the only difference is that I'm not as brave as they are. They basically aggregate information from other time to maturity, like 3 months and 1 month and so on. So I'm here just using the options with all, about the same time to maturity. Okay, so this is the only, I think, major difference. So now everybody here, in particular in this, Humboldt-University and the Great Britain areas, know how to get the state price density. State price density, according to the formula here, is the expected payout under risk-neutral world. So if you want to solve this, state price density, which is really the second derivative of call option with respect to strike price. And so that basically means that somebody as smart as Aissa, Halia, and Lowe say, well, that if that's the case, I don't need to learn stochastic processes. I could just do directly non-parametric learning, right? That's what they did, actually. So you have option characteristics. In statistical terminology, you have X, you have option price, you have Y. So you just build a non-parametric model and then just fit this directly using non-parametric methods. And after you do that, you just take 2 derivatives. So this is one way of doing. So you are really doing random search in the 5-dimensional space, or if they did do dimensionality reductions, but at least in 2 or 3-dimensional space. So this is like a no guidance. You are going through everywhere and then find a pricing formula, and completely derail from financial mathematical world, or financial or quantitative finance world. So now there's another way of thinking of this, is that the stochastic modeling. Okay, so stochastic modeling is that you crank out machinery of mathematical finance, and you have an underlying stochastic model. At the end of the day, they will, after very complicated and smart work by many people, you'll get at the end of the day the product delivered to Wall Street. Say, okay, here is the pricing formula. So the pricing formula will be dependent on option characteristics. I put a big dot here, and some unknown parameters. And then the people in the Wall Street was doing calibration, which is really saying that I put formula here, a parametric formula here. Now let me do parametric fitting, trying to find the observed price to be as matched to this theoretical price as possible. So an example of this is plenty, right? Such as Black-Scholes formula is one of these very simple and first example of this. You could enlarge, stochastic modeling by saying, okay, how about jump diffusion, stochastic volatility model, and so on. So at the end of the day, they may deliver you with this formula. Some of those are explicit, some of those are implicit. But basically, from statistical point of view, is they are really doing parametric fit to this regression problem. So here we also make a lot of assumptions, right? So we assume that the stochastic dynamic is correct in a rich neutral world, a world you and I never live, right? So the world is always live full of risk. So therefore, it's coming from nowhere. There's no validation. It's only from like a mathematical convenience. So now my question is, can we marry those two schools of thoughts? That is, people hardworking and taking that pricing formula as my first order approximation, and so this basically bring me to the neighborhood of true correct pricing, and then from then on I got my pricing error. So let's see if pricing error is completely random. If it's completely random, I cannot improve anything at all. If pricing error is not completely random, then there's a chance that I could improve this financial mathematical world. So this is really the philosophy underlying our work. That is, you use the option pricing from mathematical finance as my first order approximation. I got my pricing error, and at the end of the day, I add in things to my pricing error. Okay, so there's a lot of pricing formula in Bakshi and his collaborators' paper in Journal of Finance. So if you are interested in what the form this looks like, there are many of those. Okay. So my work today is starting from here. Is that okay? So let me introduce notation first. So let me use F star is the state price distribution rather than state price density. So it's the integral of state price density, and I put a bar on top of it to indicate what's so-called survival function. So this is the names coming from statistics on the health risk analysis, but now also being widely adopted in the credit risk derivatives. So now from here, we can easily just do change of variable. So if the interest rate times my, times my discount factor times my, option price, that would be equal to expected payoff, right? So expected payoff is integral from this to infinity of the payoff you got plus state price density. Now if I do integration by parts, so you can all see is really the price is not depend on state price density, but depend on state price distribution. And this is a very just like 5 cents integration by parts. And then the last step I'm doing here is, this is in the original scale, so I just changed to normalized scale in the mononomial scale. So from here, and this F is the future price that I defined a moment ago here. So it's just the future that I defined here, okay? Okay, so from here now we can see is that if you really care about pricing financial derivatives, all you really need is state price distribution. People say, well, big deal, integration by parts. Well, yeah, statisticians say yes, it is big deal because the state price distribution is one order derivative less. So therefore, it's easier to estimate than state price density. And you could estimate more accurately, so therefore, you price more accurately. So this is another contribution of our methodology, or observation of our methodology. Now, if I want to estimate the state price density, so that depend on which world you are, distribution, depend on which world you are live in. If you are in finance, you want me to create a portfolio has payoff function 0 and then 1, right? So the expected value of that will give me state price distribution. So if you are live in mathematical world, at the beginning I said you need to take 2 derivatives with respect to strike. Now I take 1 less derivative, so I need just to take 1 derivative rather than take 2 derivatives. Depending on which one you live on, so I try to speak more in finance language, so I'm using financial intuition rather than mathematical intuition, but at the end of the day, they are really the same. So if I long, that is, I hold stock with strike price K1, so this gives me a payoff function like this, right? And if I short, that is, I sold, or I short on strike price K2, it looks like that. And I tell you how many shares to hold, so this is just a normalization to make sure the jump here is 1. So if you're adding those together, so I got a red curve or payoff function, which looks like a step function. So expected value of this portfolio should imply the state price distribution. So in other words, the state price distribution can be inferred from this kind of this. So now to put this in more formal mathematical language, so let me denote yi be the value of this portfolio. That is, you long on K1 and short on the next closest strike price K2. So for mathematician, and then because I'm doing normalized, so it's really divided by moneyness of these 2 adjacent moneyness. Properly account by interest rate, because interest rate was here, right? That you get there. Then you could easily see mathematically this is your observed value of this portfolio is really equal to the target we wanted. That is the state price distribution, and then plus second order error. And this M bar is the middle value of these 2 moneyness. So for example, if you believe in Black-Scholes, then this F is just the log normal density, which has a very explicit formula if you like. Okay, so from here, then you could say, okay, now I know if I know non-parametric well enough, I could do directly just smoothing. Right? So you have your portfolio value yi. Now it's a long and short. And by the way, for mathematicians, there's nothing different here, right? So this just take first derivative, right? Basically, take first derivative with respect to moneyness. So if I plot all those yi's here, so on the last week of 2004, I got the green dots here. And I against moneyness here. So then people say, well, how about then I could just directly smooth this function. I got the price, so I could directly smooth on this function. I got the state price distribution, and this is what we did. So what we did here is I think the red one. So at this scale, you probably see estimating quite good. There's nothing wrong with that. However, if we go back to the pricing, again, I use 1 week data. If we go back to the pricing error, actually pricing error is quite large. So this is on the last week of December of 2004, the direct non-parametric method actually give me pricing error for the options traded, SP500 traded on that day. At the end, is $1.04. And if I use ad hoc Black-Scholes, it's $1.10. Well, there are some small difference, but not big deal. So if I do semi-parametric Black-Scholes, that is different from ad hoc Black-Scholes. The only difference is that in the fitting here, when I have implied volatility curve fit against the moneyness, instead of using quadratic, I use a semi-parametric model. Then actually pricing error substantially reduced to 35 cents. Among the options traded at 4 o'clock on that day. Okay, and if I use automatic correction or error, which I'm going to talk in 1 minute, I got only 21 cents of pricing error. Okay, so here is the non-parametric learning part. Okay, so the bad part of directly smooth this on using that smooth this directly on the non-parametrical is that if you look at this. The curvature here is very flat. It should be very close to 1. The curvature here later on should be also very flat. It should be close to, curvature should be 0, close to 0. And however, in between, the curvature is very, changing rapidly. So therefore, if you do directly non-parametric methods, just using one smoothing parameter, if you fit well here, it will not please something in here. If you please somewhere here, you will not do something there. So our idea is very simple. Let's take the main shape of this out. I take the main shape of this out, let's say using ad hoc Black-Scholes, which give me a log normal density distribution like this. So take this out. And then just the pricing error, I fit a non-parametric. So this is really the key idea that we are doing here. So that is, so in other words, what we did is, this is log normal, and this is the ad hoc Black-Scholes. So this really is ad hoc Black-Scholes formula for pricing this portfolio. And so the difference between this is the pricing error of ad hoc Black-Scholes. So going back to this picture is really, I'm really saying that I'm taking the main shape of this out by using log normal density. So I subtract that out and then trying to see what is the difference of this is, whether the difference of this is, has any structure there. And so this is really the parametric fit. The parametric fit basically is trying to say, okay, let me find the quadratic function as close, this is the theoretical price, this is empirical price on my portfolio. I try to make them as close as I can. Okay, now I'm also aware that this is whole week data, so time and maturity change a little bit. So we do a little bit engineering there, so let me not detail to that, to adjust a little bit of time of maturity change for 5 days. So this is gamma T factor accounting for time to maturity change. So at the end of the day, now I could do this pricing error by non-parametric methods, right? So this is the pricing error. This is the pricing error of ad hoc Black-Scholes formula. This is the pricing error of ad hoc Black-Scholes formula for the portfolio that I create here. Remember, the portfolio I create here is long on one thing and short on the other thing, so it's a little like a butterfly type of portfolio. So this is really the pricing error. So now the pricing error, I want to see if there's any structure, whether there's any dependence on moneyness. So I do a non-parametric fitting on the moneyness and to see if there's anything left over. So let me call my correction called FC. So at the end of the day, my estimated, portfolio value would be equal to the ad hoc Black-Scholes formula plus the correction error from here. Okay, so in other words, the state price distribution will be estimated by ad hoc Black-Scholes formula plus the state price distribution. And so this is really the underlying work for us. And before I go on further, let me see if any questions. I know that my speed always increases as I speak along. Or it's too slow, I could always even speed it faster. Is it so far so good? Okay. So so now at the end of the day, of course, then my pricing formula is very simple. My pricing formula is the ad hoc Black-Scholes price plus the correction part of my price. My correction part is the state price distribution that I learned, and this of course in the future if I discount it. So this will be my pricing formula. So in other words, so the method what we are doing here is taking Black-Scholes as my ad hoc Black-Scholes as my first order approximation, and then I get the pricing error for my for this little portfolio that I create here, which is short on one price and long on the other one. And at the end of the day, I add those together. So if you, for those people who are doing semi-parametric or non-parametric, it really is a parametric guided non-parametric estimation, right? So my first guide is taking ad hoc Black-Scholes from financial engineering or from the literature, and then I just correct it by my second order. And certainly if you say, well, ad hoc Black-Scholes is too simple, Professor Fang, you got educated, you should know something that more complicated formula that you have here. Certainly, I read a lot of literature, I'm aware of other methods, most methods would take far more computation time and talent to program, but here I just illustrate the concept. That is, you could take any Stochastic models you like, Wolfgang's one, which you have the the dynamic volatility surface. You take yours, get your pricing error and apply ours. Then at the end of the day, so the only difference here that would be Wolfgang's formula rather than my ad hoc Black-Scholes formula. Okay, so this is illustrated concept. Now, what does it look like? So again, I price using the last week for 2004. So what I'm plotting here is different time to maturity, okay? So the time to maturity, let's say the black one here is for half a year that I show you. So this looks like quite a nice picture. I mean, like decreasing functions. I mean, because the main shape is ad hoc black show, that is a log normal distribution. So it should look like that. And this may be a shorter one, maybe about 80 days here. And that would be 52 days, 24 days. So you could see the stochastic dominance of state price distribution. And that is, we know that as time to maturity increases, the price, the option price increases. So this is really reflect into the stochastic dominance of state price distribution for a family of distributions with different time to maturity. So here I'm just showing you the concept that is consistent with financial theory. That is, the longer the option is, the better the price. So translate in statistical distribution point of view is one random variable is stochastic dominant than the other random variable, and I'm showing you here exactly this kind of picture for different time to maturities. Okay, so now are there any theory back us? Yes, there is, and then I'm not going to talk detail on that. Basically is that if I apply directly non-parametric methods, you'll get the second derivative of your local approximation, the curvature of your approximation there. Now, since I take the main shape, which is log normal distribution in my case, and this is the true underlying unknown to us, the distribution that actually driven every day's option pricing. So the difference of this function, if my initial is good enough, the difference of these two functions should be small. So when you take the second derivative, this should be small. So this is really the mathematical game why you shouldn't do directly. If you do directly, I should have take second derivative with respect to the true underlying state price distribution. That would be this function. Now since I use parametric start, that is log normal distribution as my start, actually it's not log normal distribution, it's ad hoc black shows, I mean log normal distribution as my start. So you will expect this difference become much smaller now. Now you take two derivatives, usually small, so this is how you gain. So this is what I say, if you do direct non-parametric, you'll get the bias of this. So this is, this is one mathematical reason. So now you could also ask in financial econometric reason, and you could ask this every day, right? So somebody give you, let's say, stochastic volatility model, give you a pricing formula, which translate equivalently to the state price distribution of this portfolio. And remember this small portfolio, I just use finance language here, that is you long on this and short on that, and what is the price of this? That's the price of state price distribution. Okay, so state price distribution is this. So you may ask in whether the true underlying distribution is equal to this or not equal to this. So this is equivalent to testing in my situation, is saying that if correction is needed. I mean, you're asking whether the formula is correct, the same as say, okay, if do I need to do non-parametric learning and correction? And you could apply also called generalized like ratio tests, which would be a little bit, which is a little bit technical, and so it's a little bit technical. So let's not back very detailed to it, but basically it's the residual sum of squares under this null model. That is, there's no correction needed, and the residual sum of squares under the non-parametric model. So this is really generalized like ratio test. So I have over the last 5 or 7 years, I have developed systematic ideas on how to do that, and I know that this greater Berlin area has a lot of contribution to those generalized like ratio tests too, but they didn't use this as a general name. But whatever it is, so I got the test statistics, and I know the test statistics suitably normalized would be asymptotically chi-square distribution with a certain degree of freedom. So now I could ask myself, apply this testing procedure, and asking, are there, null hypothesis is no correction needed. That is, physical model is good enough, alternative hypothesis is they are not good enough. And we applied this to every day during the 3-year study that we made there, and we found all p-value is less than 1 in 1,000. So in other words, we have very strong evidence that ad hoc Black-Scholes format doesn't work from financial econometric point of view. And here is really one plot of the residuals. I mean, the pricing error of ad hoc Black-Scholes is reflected here, so you can see systematic biases. I mean, this is in one of the data we did, and this is with non-parametric learning, the pricing error looks like random or chaotic. So this is another way of talking from financial econometric point of view, that you do need correction, and after you do correction, the pricing error become, not systematic. Without this, you are always underpriced for the at-money options and so on. Okay, so of course, the judgment of the day, you can always have a lot of very nice mathematical theories. The judgment of the day is empirical studies, right? Because after all, this financial engineering, billions of dollars at stake, so of course, there needs some kind of studies, and my study is cheap. Basically, my collaborator and I, so nobody pay us any penny, so we just do it. Okay, well, Princeton University does pay me something, but other than that, nobody pay me anything. So, it's SP 500 options traded on those 3 years period from 2002 to 2004, and the data is downloaded from Optionmetrics data, and we select options to be. We select over 100,000 options that satisfy our selection criteria, which basically says that maturity shouldn't be too short, because too short, 5 days means a lot. Remember, I aggregate data in 5 days. So we between 20 days to 240 days options, and implied volatility should be no more than 70%. So I don't want to do those highly illiquid trade options, which skew the whole studies. And the absolute price of options should be at least 1/8. That is 12.5 cents. Right? So there are, of course, in all empirical studies, there's a large database. There's a lot of challenges here. Like, for example, temporal mismatch. Option is traded, let's say, in Chicago, and the stock SP 500 is traded in New York exchanges. So, matching these two databases is a challenge. So, temporal mismatching would be one of the problems. There are also another problem is what's so-called illiquid trade options. For example, deep in the money options, like today's stock is $10, or today's, let's say, SP 500 is $1,400, and your option is, let's say, 1,000. It's deep in the money, so that in other words, work like a stock, so nobody really traded much. And how do I account dividends raised paid by those 500 companies? So it's very difficult to match those in practical terms. So our resolution is very simple. This is follow the study of Aisa, Halia, and Low. So we basically only use daily closing prices. Okay, so daily closing prices is closed at 4 o'clock in New York and 3 o'clock in Chicago. Just match perfectly nice for us. So, and we use the put call parity to infer the deep in the money options into, to translate put option into call options, just to increase the number of data for illiquid trade deep in the money options. So, and the empirical findings, whether you're separating or not separating, are the same. So this is how we actually aggregate those information. And the future price is also implied from this option, from this formula. From this formula, we just take the most liquid money, that at money options, and you back out this future price here. So I got the future price too. Just solving this equation, you got the future price too. So we have every number at our own, let's say at our own, let's say discretionary. So depending on how you use it. So now I stratify my options into 15 categories. So short-term time to maturity, which is 60 days to, less than 60 days. Middle-term time to maturity is 60 days, 2 months to half a year, and more than 160. So basically divide data into 1/3, 1/3, 1/3. Okay, and then we also divide the moneyness into 5 categories. Deep in the money, that means moneyness less than 0.8. In the money, at money is moneyness between remember, all stock in my studies, in moneyness is $1. Right? So this is really like trade between 94 cents and $1.05. 4 cents. Okay, this is at money and out of money and deep out of money. And so there are a lot of options here. So for example, there are 6,300 options here. And the average price is, let's say, $323.22. And the implied volatility is 44%, 43.91%. Okay? So if you look down this way, implied volatility, bigger, smaller, even smaller, bigger again, bigger again. So it's really a smile, right? Implied volatility smile. And the same way if you look at middle term, implied volatility smaller, bigger, smaller, smaller, bigger, bigger, right? So again, implied volatility smile. So implied volatility smile is certainly very evident in the financial markets. And so here is the in-sample performance. So I basically summarize into 2 categories. One is absolute pricing error in dollar term, and the other is relative pricing error in percentage term. Okay, so here is the absolute pricing error. And the absolute pricing error, so there's a lot of numbers here. I compare 3 methods. 2 methods basically is ours. One method is ad hoc Black-Scholes. Actually, we compare 4 methods, and the other one is Scotch. Take a lot of time to run computer, but there's no room I could present here, so I just do 3. So let's look at the most typical one. So what's most typical? Most liquid one is M-money trading. And let's say look at middle term. So I just look at the 3 by 5, 15 cells. I look at right in the middle, right? So our methods have 38 cents of error or among 100,000 options that we studied. Well, in this category it's less than, maybe around 6,000 or something like that. And the total is 100,000. If I add in 15 cells together, it's 100,000. Okay, and then Sarah per measure method has pricing error of 76 cents, and it would be $1.46 if I use ad hoc Black-Scholes. So the improvement is quite radical. And the same, you look at this. So what is, the red one is always indicate that our methods and our method is better. And the green one is ad hoc Black-Scholes, and the black one is our semi-parametric. That is, you fit a non-parametric curve to imply volatility as a function of moneyness. So it's quite evident. So what we really do wrong, as I would expect it, would be in the short-term time to short-term maturity, and particularly in deep out of money, because deep out of money there's illiquid trade first of all, and secondary, if it's short-term, let's say only 20 days, 5 days of aggregation data make a lot of difference, a very large noise there. So this is really in absolute value terms. And so now in percentage terms, the pattern looks really the same, just the number difference. So let's look at the at money options again. And this is, again, that the method of performance is our ACE. That is, I do estimate state price distribution. I create a portfolio, synthetic portfolio. And then I use log normal as my theoretical price. And then I get in the pricing error, and I correct the pricing error, add back to it. So this have like 1.3% pricing error compared to 6% error of ad hoc Black-Scholes method, and 2.3 of our second best methods, semi-parametric Black-Scholes. So if you are do a little bit out of money, that percentage getting even larger. We have about 9% because out of money option is very cheap. So the denominator is small. So I have 9% error, and our second method have 58. So it looks quite bad in this one. Oh, ad hoc Black-Scholes, I'm sorry, quite bad. Now I switch a method Gauch. Gauch has 37.97. Percent error, and so on. So the whole pattern looked the same. Then I think Ray must say, Jianqing, don't you know how to plot a picture? And of course I say, okay, I did. I did last night. I know Ray is here. He must raise this question. So, but I tried to put in the slides. I didn't have enough time. So let me just show that so that Ray will not complain that I don't know computer. Okay, so this is the. The same thing that I will talk about there. There's a lot of number that we've seen before. Now I just plot in the picture. So this is for the short-term time to maturity of, this method is our method, ACE method. So this is the pricing error in absolute dollar terms. And this is the Gauch methods. the pricing error for like, we have 5 moneyness, right? So, 5 categories of money, deep in money, out, so I have 5, deep in the money, and money, out of money, deep out of money, and so on. So I have 5. So this is really the pricing error of gauge. This is the pricing error of ad hoc Black-Scholes, and this is pricing error of our semi-parametric Black-Scholes, and this is our, our ACE method. So these black and the blue basically are our methods. And I know that for time to maturity is short, our method doesn't work well, as I admitted at the beginning, particularly for deep out of money options, and this can be seen here. So this one is really the same plot, except now I'm doing in percentage term. And in percentage term, again, the number different, but the value looks very similar. So now if you look at the maturity, midterm time and maturity, so this is our methods, okay? And this is our second best methods, and this is ad hoc Black-Scholes, and this is gauge-based methods, okay, in terms of pricing. And the same thing. So if you download the paper actually have these pictures. I didn't just forget to, I forgot to include that. Okay, so this is the same for, the long-term time to maturity, and so on. Okay, so this is really the in-sample performance. Yeah? Okay.